Okay, welcome back. We'll continue now with working with the finite dimensional weak form, or the Galerkin weak form. What we saw in the last segment was a digression to say more about what we meant by function spaces and to understand why this might be important for us. Okay, because and you recall that we defined function spaces as being useful, or we introduced function spaces as being useful in order to give us a sense of control over the functions themselves and over their derivatives, right? So when we say that we have control over the functions, we are saying that the functions are bounded. When we have control over the derivatives, in addition to the functions, we have this notion of regularity, right? That the functions are sort of smooth and so on. Okay, and we saw that through examples. Okay. With that as background now, we will actually launch into the finite element method for this 1D linear elliptic PDE. Okay, and this will be, and we are going to work off the Galerkin or the finite dimensional weak form. In this segment, we are finally looking at the finite element method for linear elliptic PDEs in one dimension. Now, we're going to work off the Galerkin weak form. Okay, recall the Galerkin or the finite dimensional weak form. One more time, unto the breach. Okay, so one more time, we're going to write this out. Find UH belonging to SH, which is equal to SH is equal to functions UH. Now we're saying that they belong to H1 on 0, L, such that they satisfy our Dirichlet boundary condition. Okay. Now, gratifyingly, we know what H1 means. So we already have an idea of the extent to which we've restricted our search for solutions to this PDE. Okay, so recall all the functions we talked about in the previous segment. Those are the sorts of functions we are now considering as candidates. Okay. Okay. Actually, for this reason, UH is often also called the space of trial functions. Okay, so often UH is also called a trial functions because we say we're going to try out all these functions living in SH. Okay, so maybe that's a useful thing to say here. Okay, find UH belonging to SH such that for all WH belonging to VH, which is also drawn from H1, okay? Such that for all WH belonging to VH, the following holds. Integral 0 to L WH comma X sigma H A dx equals integral 0 to L WH F A dx plus WH at L T A. Okay, that is our finite dimensional or Galerkin weak form. Now, one thing I should point out here is the following. In our finite dimensional weak form, observe that we have sigma h, right, in that finite dimensional weak form. What we imply is that sigma h is going to be obtained as E U H comma x. Okay? However, f, our forcing function f, is given to us as data. So we assume, and in fact we will in fact use the fact that in our implementation of the finite dimensional weak form, we are not going to attempt to approximate the data, right? We're going to represent the data exactly as given to us. So f of x is not finite dimensional. Okay, f of x will actually be represented as it is given. Okay, in this sense, you may think of it as it's not exact, but the fact that it is data is why we're not going to represent it as a finite dimensional approximation. Right, it's given to us. Okay, all right. And of course, in this case, does the question arise for T, the traction? Think about it. It doesn't in 1D, because in 1D the traction is applied at a point. So the question of whether we approximate it, whether we write it as finite dimensional or not, doesn't really arise. When we go to higher dimensions, when we go to three-dimensional problems, we will see that there is a question to be answered for the traction. Okay, because the traction will then be defined on a surface and so on, but we'll get to it when we do. Okay, so T, let me just state, is a point value. Okay, and I'm stating all these things for us to understand why in our finite dimensional weak form we have finite dimensional versions of WH. We also have a finite dimensional version of sigma H. Right, and this is because sigma h is going to be obtained through our constitutive relation applied to the gradient of the finite dimensional trial solution, UH. Okay? And on the right-hand side, again, the weighting function is finite dimensional. Not so for the forcing function, which is data. And it's actually not a relevant question for the traction in this 1D setting. Okay, so that's what we have, right? So that explains why we have finite dimensional forms of WH and sigma h. All right, so we can write out this finite dimensional or Galerkin weak form if we say how we obtain our finite dimensional functions. Okay, so that's really the question. How do we obtain UH and WH, right? Alternately, how do we obtain SH and VH? We need to define those, right? We need to say what kinds of restrictions we are using on our finite dimensional functions, okay? In one sense, the finite element method could be thought of as simply defining what these finite dimensional approximations are, okay? So here's how we do it, okay? The way we do it is to, I'll write the statement here and then I will start sketching things. What we do is partition 0, comma L into finite elements okay, which are disjoint subdomains of 0, comma L. All right. Okay. So here's how it goes. Let me just draw our bar one more time. And here we have our x-axis. That is L, that is 0. Now, for brevity, as well as to make an easy transition to multidimensional problems, I am going to introduce notation here for this domain 0 to L. I am going to write omega is our open interval 0, comma L. Okay, so that is our general domain. Okay, so the way finite elements proceeds is to partition our domain omega into subdomains, right, which are our elements. And this partitioning is done by nodes that I have, that I'm now marking here. Okay, so we look at these nodes as being defined as x, we call this x sup 1, x sup 2, and so on, x sup n, right? Sorry, I shouldn't call that n. I'm going to use that for something else. I'm going to call this x sup, call this actually x big K, because I am going to call this very last node x sup n. Okay, or I think I'll even call it x sup number of nodes. Okay, all right. Now, each of these subdomains that we've thereby defined with these nodes, these are going to be our elements of the finite element method, are omega 1, omega 2. In general, we have omega e, right, and so on. Okay. Observe that what we've done here is what the partition that we've introduced is the following. We've partitioned omega into subdomains omega e, all right? And the nature of this partition is such that the total, that our entire domain omega is the union of each of these subdomains omega e, right? Furthermore, each of these subdomains omega e is an open subdomain. Okay, it's an open interval, right? So The total domain omega is the union E equals 1 to n sub EL, which for very obvious reasons is number of elements. Okay? So the domain omega is the union of each of these subdomains omega sub E, and E here runs from 1 to NEL. Now, because omega E is open, okay, and because we have a very convenient one-dimensional setting, what you will note is that each omega E is the open interval x sup E to x sup E plus 1, right? Clearly, because omega 1 is the omega 1, which is this one, is the open interval x1 to x2 and so on. Okay? So, now there's one more thing we need to do here for technicality. Because each of these omega E's is an open interval, and because we would miss out the intervening, the inter-element nodes if we just went with this union, we need to say also the following. We need to apply closure to this union, okay, and say that once we close that union, we also have a closure of our open interval. Okay, so this way we're making sure that we are not missing any points. This is for purely technical purposes. When it comes to computing, it makes no difference because each of those points is what we call a set of zero measure. Okay, so let me just state the notation here. So omega bar is the closure of omega. All right, so it is basically saying that omega bar equals omega itself union the boundary points of omega, which to introduce even more notation is written as that. Okay, partial of omega refers to the boundary of omega. These are purely technical points, but it's useful to state these now so that there's no confusion later on about what we're doing with nodes and so on. Okay? All right. So, we have this partition. Let me introduce terminology which I've been using already, but let me define the terminology. So, the points xe are the nodes of the partition. Right? Omega E is an element. Okay? Obvious notation, obvious nomenclature, which I'm sure you all either knew or figured out or anticipated or whatever, but here it is. Okay? All right. So how do we first use this partition? How do we begin using it? As a very first step, we observe that our weak form is stated as an integral. Okay? And what that lets us do is to write that integral as a sum over the elements, right, over the subdomains of the partition. Okay, so the weak form, or the Galerkin weak form, but this actually holds for the infinite dimensional weak form as well. Right, the Galerkin weak form, we will now write as follows, right? Instead of writing it as a sum over 0 to L, we will first write it as a sum over omega. Okay, WH comma X sigma H A dx equals integral over omega WH F A dx plus WH at L T A. Okay? So we've gone from writing it as an integral over 0 to L to an integral over omega, purely notation. The next thing we can do now is to write this as an integral over each element, subdomain, okay? Like that, okay? But note that we need to get to all of omega, right? So here we take a sum over E, okay? Where E runs over all the elements, 1 to NEL, 1 to number of elements, okay? And here too we have sum E equals 1 to number of elements, integral over omega E, WHFA dx plus WH at L T A. Okay, so this is the first thing that our partition of the domain into elements, subdomains lets us do. What the next step that it also makes possible for us is to now think in terms of defining our finite dimensional functions, but observe that having reduced those integrals to integrals over smaller subdomains, really all we need to worry about is how to represent these finite dimensional functions over the subdomains omega E. Okay, so let me just write that here. So represent SH and VH over each omega sub E. Okay, so we can really afford now to focus on what's happening within each element, within each subdomain, right? With the idea being that the union of the subdomains gives us the entire domain that we're interested in, and thereby we can also define our finite dimensional functions over the entire domain, okay, by going to these subdomains. Okay, when we it's useful to stop here. When we return, we will think in terms of how we define these functions over the subdomains.